Our circuit of interest for today will be this guy, where we have a 12-volt source connected to a 3-ohm resistor. Call this terminal A of the system, this guy terminal B of the system. This will be a 1/2 ohm resistor. We have a switch that is closed at position A at t is equal to 0, and will be, or 0 minus, and we'll be closing at position B at t is equal to 0 plus. And then we have a 0.25 farad capacitor over which a voltage drop of Vc of t occurs and a current of Ic of t flows. And over here, we will have an inductor having a value of 2 henries over which a voltage drop VL of t occurs and a current IL of t flows. And then we have a 1 ohm resistor like so. And our goal here will be to determine capacitor voltage Vc of t for all time greater than or equal to 0 plus. All right. So let's start by just looking at this thing and figuring out which of our 3 types of circuits it is, right? So is it a series RLC circuit? Is it a parallel RLC circuit, or is it a general RLC circuit? Luke, you have any thoughts? All right, explain your reasoning. Okay, so there's a couple of things I didn't care for in your response. We only consider whether this is a series, parallel, or general during the transient condition. So what it looks like prior to the transient condition is completely and utterly inconsequential. During the transient condition, where the switch is closed at B, I think you said that the capacitor and the inductor are in series. I disagree with that sentiment. I also disagree that the 1 ohm resistor and the 1/2 ohm resistor are in parallel. We have a branch containing a resistor in parallel with a capacitor, in parallel with a inductor that's in series with a resistor. And since not everything is directly in parallel, and literally nothing except the inductor and 1 ohm resistor are directly in series, this obviously can't be a parallel RLC circuit or a series RLC circuit. Are we going to have to analyze this guy at t is equal to infinity? No, because our only independent source, this 12-volt source over here on the left, is actually being taken out when that switch changes state. So since there are no independent sources present during the transient condition, this is obviously then a natural response problem where we only need to solve it for t is equal to 0 minus and potentially t is equal to 0 plus. So with that in mind, during the transient condition, so for all t greater than or equal to 0 plus, our circuit looks like this, where I'm going to call our 1/2 ohm resistor R1 Our capacitor will be C. Pardon me. Our inductor will be L. And our 1 ohm resistor over here will be R2. I'm going to write down all of those relationships momentarily. This is VC. This is VL. This is IL. This is IC. So just to reiterate, we have R1 is 0.5 ohm. R2 is 1 ohm. C is 0.25 farads. And L is 2 henries. Okay. So when we are coming up with our second order differential equation, it's important that we're doing it during the transient condition, which means we need to start by looking at what's happening during the transient. So based on our limited amount of expertise that we developed in class on Monday, if today's Wednesday, Alexis, how do you think we should begin to develop our differential equation?
Add the parts together.
Okay, so apply Kirchhoff's current law at that top node would be the place that I personally would do it. Okay, so how can we express, so that will be simply summing this current, and this current together, right? So the first question that I want to ask any of you is how we can express the current flowing through the resistor R1 in terms of one of our quantities of interest, either the inductor current or the capacitor voltage. Mr. Shepard. Or, sorry, not Shepard, Smith, Christian Smith, right? Exactly right, just VC over R1. So we'll have VC of T over R1. The current flowing down is IC of T, obviously, which we could express in terms of the capacitor voltage as, Justin? How do we express this capacitor current IC as a function of the capacitor voltage VC? Anybody else remember the IV relationship for capacitor? C dV by dt. And then directed to the right, we have our inductor current, IL of T. We'll set all of these guys together, and let's call this equation 1. There wouldn't be any, there's no harm in doing that, but I'm just doing Kirchhoff's current law, so I don't need a ground. All right, Caleb, what do we do now? We have one relationship that has the capacitor voltage and the inductor current tied together. Where are we going to get a second one? Yeah. KVL, okay, where? The right-hand side loop. Okay, sure. So KVL at the right-hand side loop is going to give us our capacitor voltage VC is equal to our inductor voltage. So how do I express my inductor voltage in terms of my inductor current? L di by dt. Yep. And then we're going to have the voltage drop over our resistor, which is just going to be R2 times IL. Call this guy equation 2. So it should be fairly obvious here that I could substitute in this expression for VC directly here. So the only thing that I really need now is a relationship that puts the derivative of the capacitor voltage in terms of either the inductor current, the derivative of the inductor current, or the second derivative of the inductor current. So Sarah, where am I going to get that derivative of the voltage relationship? By taking the derivative of the voltage relationship, okay? So I'm looking for dVC by dt in terms of something having to do with IL. So if I take the derivative of this guy down here, that's going to give me exactly what I want. So that'll be L times the second derivative of IL with respect to time plus R2 times the first derivative of IL with respect to time. Call that guy equation 3. And now it should be fairly obvious that if I substitute 2 and 3 into 1, I'll have my second order differential equation, no problem. So if I divide VC by R, that's going to give me L over, divided by R1, L over R1, the derivative of IL with respect to time by dt, plus R2 over R1, IL as a function of time, plus C times the derivative of the voltage with respect to time. So I'm just going to substitute in directly here. L times the second derivative of the inductor current plus R2 times the first derivative of the inductor current, and then plus IL is equal to 0. And now I can group like terms. So I'll have LC times the second derivative of the inductor current plus L over R1 plus R2C times the first derivative of the inductor current plus 1 plus R2 over R1 times IL of t equal to 0. And from here really is kind of good enough to figure out what alpha and omega naught are. We know obviously that we should divide this whole thing by a factor of LC to get rid of our coefficient on the second derivative term. And so what we will find is that alpha is going to be L over R1 plus R2C divided by twice LC, and omega naught will be the square root of 1 plus R2 over R1 divided by LC. Is everybody okay with what I did there for calculating alpha and omega naught? I skipped a small step that I hope is fairly obvious. So let's take a moment to plug in our values and calculate what these coefficients are. So let me scroll up here. So we're going to have 2 henries divided by R1, so 0.5, plus R2, which is 1, times C, which is 0.25, I believe. Yeah. That whole thing divided by 2 times L times C. So I get alpha to be 4.25 nepers per second. Omega naught, I'm taking the square root of 1 plus R2, which is 1 ohm, divided by R1, which is half an ohm, over L, which is 2 henries, times C, which is 0.25 farads. And I accidentally hit the clear button, so now I have to redo all of that. And I get 2.449, so let's call that 2.45. Radians per second. All right, so since alpha is greater than omega naught, this is obviously an overdamped circuit. So while we're at it, let's go ahead and calculate S1 and S2 because we know that we're going to need them. S1 is negative alpha plus the square root of alpha squared minus omega naught squared. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. And so I get negative 0.777 per second for S1. And negative 7.723 per second for S2. We all on the same page here. Okay. So now we need to do our analysis at t is equal to 0 minus and t is equal to 0 plus, which should be pretty straightforward. So at t is equal to 0 minus, our circuit is going to look like this guy, where we're going to have our 12-volt source, 3 ohm resistor. The switch is closed at position A, which means the half ohm resistor is just kind of dangling, so I'm not going to bother to draw it. Here is our capacitor voltage, VC at 0 minus. Here is our inductor, IL at 0 minus. And we have our 1 ohm resistor. And here is VL at 0 minus. Here is IC at 0 minus. And so we need to determine these quantities. All right, so Cheston, what should my inductor voltage at t is equal to 0 minus be? I disagree. So 0 minus represents DC steady state, which means our inductor is a short circuit. A voltage drop over a short circuit is always 0. So the answer to VL at 0 minus should literally always be 0 volts. Mr. Bodie, what should the value of my capacitor current be at 0 minus? And this is another thing that will always be true. 0 amps, right? Because our capacitor looks like a short circuit at DC steady state. So the only things that we should have to do any analysis on potentially is the capacitor voltage and the inductor current. So you had mentioned, Justin, doing some sort of voltage division. That would be appropriate to determine the capacitor voltage. So do that voltage division and tell me what the answer is. Okay. So
in this case, it would be better to find the current first.
you know, 6 of one, half a dozen of the other, right? So what I mean by that is the potential difference between this point in the circuit and this point in the circuit is 12 volts. And we're looking for the drop over a 1 ohm resistor when there is a total series resistance of 4 ohms. So it's just 12 times 1/4 is 3 volts. And then from that, we know that there must be 3 amps of current flowing through the inductor, or as Brandon suggested, we could do it the other way around. We could see that the 12 volt source sees a total series resistance of 4 ohms, which means there is a current of 3 amps flowing around in the circuit, which would be IL. 3 amps times 1 ohm gives us 3 volts. So the order of operations here doesn't matter. They're both equally not difficult. IC current, DC, IC, VL, IL. Let me try to make this C more obvious than it is a C. All right, so any questions regarding our analysis at T is equal to 0 minus? All right, so at T is equal to 0 plus, the 12 volt source and the 3 ohm resistor have been disconnected. So we are left with our half ohm resistor over here to the left in parallel with our capacitor. Since the capacitor voltage was 3 volts, I am going to model that as a 3 volt source having the same polarity as VC. Our inductor current was 3 amps, so I'm going to model that as a 3 amp source having the same direction as IL. And then here is my 1 ohm resistor. This guy right here is VL of 0 plus, which is an unknown quantity. This guy right here is IC at 0 plus, which is also an unknown quantity. So we have VC at 0 plus 3 volts. IC at 0 plus, we don't know. VL at 0 plus, we don't know. And IL at 0 plus, we do know. All right, so how can we determine either of these two unknown quantities?
The current through the 1 ohm resistor. So we can find it both in the KPO on the right. We can both cross the current source.
Okay, so if 3 amps of current is flowing through the 1 ohm resistor, then that means there is a voltage drop of 3 volts across the 1 ohm resistor. Positive polarity on top, negative polarity on bottom. Everybody okay with that? So if we apply Kirchhoff's voltage law around the right-hand loop, we'll have -3 volts plus VL plus 3 volts is equal to 0, which means VL has to be 0 volts. IC, we can get using Kirchhoff's current law at that top node, right? So since this 1/2 ohm resistor over here on the left has a 3 volt drop over it, what's the current flowing to the left and down through the 1/2 ohm resistor? 6 amps. So we have 6 amps plus 3 amps plus, excuse me. Yeah, 6 amps plus 3 amps plus IC is equal to 0. So what's IC have to be? -9, right? Did I do that math incorrectly? No, yeah. So we know the current leaving here. Let me write it down.
The voltage of the capacitor current and the inductor voltage just before the transient condition.
Not really. So actually ask that question again, because I want to make sure I'm told you correctly. We do not need to know we do not need to determine these quantities because they're given to us, but they don't really influence what's going on at t is equal to 0 plus anyway. So what we need to find at 0 minus is the capacitor voltage and the inductor current, because that tells us how the capacitor and inductor are behaving respectively at t is equal to 0 plus. But we don't have to do any work for these anyway, so I just write them down for all parts, because that's the habit that I've developed. All right, so 6 plus 3 plus IC is equal to 0, which means IC is -9. And because this circuit does not contain, so at t is equal to 0 plus, actually, that's a little wonky, so I don't want to talk about that quite yet. So during the transient condition here, we can see that there were no independent sources, which means we don't need to do any analysis at t is equal to infinity. So we're ready to set up our systems effectively and solve for our unknown coefficients A1 and A2. All right, so let me ask you guys a question. My ultimate goal in this problem, I believe, as I outlined at the very beginning, was to determine the capacitor voltage as a function of time. Is that correct? Okay. The second order differential equation that we developed was in terms of the inductor current. Is that a problem? Absolutely not. We're going to get literally the exact same values for alpha and omega naught if we had done different substitutions and gotten a second order equation in terms of the capacitor voltage. We would literally get the exact same response. It has to be the same in both cases because this is a linear network. All right, so we know that VC of t will be of the form A1e to the S1t plus A2e to the S2t. So at 0 plus, this is just going to look like A1 plus A2. And since the voltage across the capacitor at 0 plus was 3 volts, we have A1 plus A2 is equal to 3 volts is our first equation. Easy peasy, right? We know that our inductor current, IC of t, will be of the form C dV by dt, which is going to look like C S1 A1 e to the S1 t plus S2A2E to the S2T. So at T is equal to 0 plus, this reduces to C S1A1 plus S2A2. And from this, we have 0.25 farads times S1 negative 0.777 A1 plus C 0.25 farads times S2 negative 7.723 per second. A2 is equal to our capacitor current at T is equal to 0 plus, which was negative 9 amps. There is our second equation. So we can solve this system. And so I have 1A1 plus 1A2 is equal to 3. And then I have C times S1, which I stored in my calculator as variable C. Plus C times S2, which I stored in my calculator as variable D, is equal to negative 9. I get A1 is equal to negative 1.847 volts. A2 is equal to 4.847 volts. Anybody else get those numbers when they solve their system? Wonderful. All right, so from this, our capacitor voltage, VC of T, is equal to negative 1.847 e to the minus 0.777 t plus 4.847 e to the minus 7.723 t volts. So now I'm going to get my keyboard, start up LT Spice so I can simulate the video. Or why my computer didn't turn off per se, but all right. So I'm going to pull up LT Spice here if I can find it in all of, oh, it's behind this, of course. And it's being weird about the sharing, so let me go ahead and fix that. All right, so when I simulate these circuits, I'm simulating the circuit during the transient condition. So that allows me to not have to worry about setting up switches and making sure they're behaving correctly. It does force me to have to give my capacitors an initial voltage and my inductors an initial current. So during the transient condition, our circuit looks like this. We have two resistors, a capacitor here in the middle, an inductor like so. And let me wire this guy up. Let me put in my component values. And I always choose to put my ground terminal on the negative polarity terminal of the capacitor. And I do that because that's the easiest way for me to set the initial condition for the voltage drop across my capacitor. Because if I try to do just V open parentheses C1, it does not know how to interpret that because it's not taking it as a node, right? LT Spice works only with a nodal voltages effectively, okay? So if I mouse over the positive polarity terminal of my capacitor, which should be this guy up here, you may not be able to see this, but it says this is node N001. So when I do my initial condition, I click this .op button up here, and I type .IC, stands for initial condition, V, the voltage at N001, which is the voltage at the positive polarity capacitor terminal with respect to ground at T is equal to 0 plus. That should be equal to what? What did we determine it to be when we analyze a circuit at T is equal to 0? 3 volts. So I just put the number 3. Now I'm going to type Control M to start a new line so that I can put both initial conditions in a single command. So I'll have .IC. So LT Spice, as we've mentioned before, handles currents only through components. So since there's only one inductor in this circuit, I'm just going to do I for current, open parentheses, L1, because I want the current flowing through my inductor. What was the initial condition on my inductor current, or what was the value of IL at T is equal to 0? 3 amps. IL at T is equal to 0, not IC, right? We're going to let this system handle everything else. The only initial conditions that we can put in is the capacitor voltage and the inductor current. We can't put in anything else. LT Spice will freak out and tell us it's not allowed. So the initial condition on the inductor current was positive 3 amps. All right, and I'm just going to take a total stab in the dark here and run my transient simulation for 10 seconds, knowing good and well that I'll probably change that shortly. Okay. So my capacitor voltage I get by mousing over the positive polarity node. And that looks pretty reasonable. All right, so I could maybe shorten it up to 7 or 8 seconds, but that should be okay. All right, so what I need to do now is check my analytical solution versus that of the simulation, which I get by right-clicking in the plot area and adding a trace. One thing, I'm not going to do it here, but I asked you to do it in your design project number 1 thing, which has been uploaded to Moodle, by the way. I don't think I set a due date for it, but I'll get around to doing that shortly. You can add multiple plot planes. So if you wanted to look at 2 things at the same time, but not necessarily plotted on the same plane so that you don't get weird graphs, you can just add multiple plot planes into this plot and look at things that way as well. So that if you were, let's say if I had asked you to do not only the capacitor voltage, but also the capacitor current, you could do 2 plot planes, one with the voltage, one with the current, and then you could type in a mathematical expression for each of them so that you don't have 4 things on the same plot. You have only the voltage and its mathematical representation on one plot, only the current and its mathematical representation on the other plot. So just a heads up, you can save yourself setting up multiple graphs and all that kind of crap by doing things. All right. So we add traces, and down here where it says expressions to add, I can type in my expression, right? So I had negative 1.847 times exp of negative 0.777 multiplied by time. And I got to do my parentheses in the right direction, plus positive 4.847 multiplied by exp negative 7. What was S2? 7.723 or something like that?
Yeah, 72.
Multiplied by time. And the two graphs overlap and the scales are identical on the left-hand side and the right-hand side, which means our analysis was correct. So all that differential equation crap we did at the beginning, we must have done it correctly because that allowed us to calculate alpha and omega naught, which in turn allowed us to calculate S1 and S2. And then the results of our more straightforward analysis were pretty easy. And so we can tell we did everything right. Huzzah. Questions about simulation? Sonny.
So you always just treat the circuit as a transient state?
In the transient state, because we are trying to determine how it behaves during the transient. If we wanted to be, I don't want to say necessarily lazy, but if we wanted to make sure that our analysis of the circuit at t is equal to 0 minus or correct or something like that, or figure out how to get those initial conditions easily, we could plot the circuit during that DC steady state condition and use a DC analysis to determine our inductor current and our capacitor voltage, right? Because that's at t is equal to 0 minus, it's just a DC circuit. So LT Spice will interpret all of the inductors as short circuits, all the capacitors as open circuits, and then it'll do the analysis for you to figure out what VC is and what IL is. So you can check your answers there. And then obviously you could just do DC analyses for what's going on at t is equal to 0 plus by doing a DC analysis of the circuit, where you're putting the initial conditions, actually no, you're representing the capacitors by the voltage you find at t is equal to 0 minus, and the inductors by a current source that you find at t is equal to 0 minus. So you can do everything piece by piece using DC analysis, but when we want to know how this guy functions because of the time decay and everything, we have to be doing a transient analysis. And so that means we have to just be looking at the circuit during the transient condition. Any other questions? Brandon?
Project, do you want any special kind of formatting for the project? Or
No, just like a homework kind of thing. Yeah. Anything else? Sonny?
You said that the general RLC circuits weren't going to be on the take-home portion?
No, they will not be in the in-class portion. They will be on the take-home portion. So the in-class portion will only be either series RLC or parallel RLC. So my intention for the in-class portion of your exam on Friday will be one circuit. That is a series RLC circuit. And it may be so there's going to be one circuit that will be series RLC, one circuit that will be parallel RLC. One of those two circuits will have something going on at t is equal to infinity, and the other of those two circuits will have a dependent source in it. So it's literally just going to be two circuits that I'm asking you to analyze. And so you're going to be given points for correctly identifying alpha, omega naught, and then how it behaves at t is equal to 0, t is equal to 0, t is equal to 0 minus, t is equal to 0 plus, and then t is equal to infinity if appropriate. And then figuring out what the coefficients of that transient waveform are.
Like the homework case.
Exactly. There's literally nothing I can ask you other than the exact same thing I ask you on the homework assignments. Like there's nothing else to know about transient analysis. So a reasonably straightforward pair of problems, one of which will happen to have a dependent source and the other of which will happen to leave an independent source in during the transient conditions so that you have to analyze things at infinity.
There's no responsive question during.
Not at all. Nope, just two problems.
Should we expect to see our exam 1 grades before we take exam 2?
Honestly, probably not. You know, you should expect to see your exam 1 grades after this long weekend when I get off my ass and grade them. Yeah, sorry. I have to spend tomorrow making out your test. So coming up with two problems that I feel like that you all can actually complete in an hour and 15 minutes without a wild amount of difficulty or anything.